Hello everyone, I'm Deepika, a PhD student from IIT Hyderabad, and our paper is titled LogicCBMs, Logic Enhanced Concept-Based Learning. Interpretability has become imperative, and a big reason for this is that we can't have black box models going and getting deployed in high-stakes applications like criminal justice and healthcare because people's lives depend on these decisions. Even more so, there's been a shift towards inherently interpretable models owing to the various drawbacks that post hoc methods have. And concept based models have emerged as a particularly promising direction in this category. Now, in a classification setting, the model usually learns a mapping from an image space to a label space, whereas in concept based models, it breaks down into this two-step process where inputs are used to learn concepts and concepts are used to learn the class. So for an input image, we would classify this as a cat because it's furry and it has whiskers. The concept to class mapping is usually just a linear layer, and the reason for this is simple. It's for interpretability purposes. Because if it's a linear layer, we can just look at the weights and see which concepts are strongly associated with which classes. However, this is limiting, and we can't really capture the rich relations between concepts with a linear layer. And an example that really brings this forth is Arctic foxes. Arctic foxes can have either white or brown fur based on environmental conditions, and there's no way that a linear layer can capture such nuance. So the main question that we ask in this work is how we can go beyond this linear concept to class mapping while importantly retaining interpretability. And our solution to this is to use logic gates. So we can express this as white fur XOR brown fur. And this is exactly what we do. We take a concept-based model and we add these learnable logic gate layers over the concepts. This enables us to obtain logical compositions of concepts, which we refer to as predicates. And now our goal becomes to learn the set of predicates logically entailed by each class. So our method is composed of two steps. So we firstly have concept pairing, for which we use the CP matrix that we introduced. This gives us a pool of concept pairs. And we also have a G matrix that gives us the logic gates. So next is differentiable logic learning. So logic gates are non-differentiable. So we use their fuzzy logic alternatives. So here not friendly becomes 1 minus friendly. Fur and whiskers become fur into whiskers, and so on and so forth for the various logic gates that we have. So now what we do is, for each logic neuron, there are weights associated with each possible logic operation that it could be. And we do a weighted predicate activation, we compute this, and then we forward pass the maximum of all of these to learn the final linear predicate to class mapping. We see that logic improves multiple aspects of a model. They perform better, they give better concept alignment, they perform more effective interventions, and they capture meaningful predicates. And how do we go about measuring this? Because we don't really have this notion of a logic ground truth. And such information isn't really practical to obtain for our real-world benchmarks. So we use synthetic datasets where we know the data generating logic. And we do this evaluation over XOR, 2XOR, and clever logic, where the last two datasets are introduced by us. These are some examples from the clever logic dataset, where we specify the logic expressions for each class. For example, for this one, the generating logic is cube XOR sphere. So each image in this class either has a sphere or a cube, but not both and not neither. And it's similar for all the other classes. So we input these images and we learn a logic CBM where the concepts are the shapes. So we compare our misclassification rate with the DCR baseline, which is another concept-based logic method, and we see that we do much better. We also introduce a worst case metric for CBMs, but for this video, that is all. Thanks for watching, and please check our paper for more details.